I do hope that you had a very good lunch break with a lot of discussions and good food. So now it's time to get back to our regular sessions. So my name is Peter Szegedy. I'm with Serena. I'm one of the project development officers. I'm looking after some crowd-related aspects of the community. So you probably know me if you're attending TF storage meetings or Serena networking conferences in general. We have the session titled Emerging Cloud Stacks. We have 4 speakers lined up, and basically they are covering 3 different approaches to the same problem. So the first speaker will be Andrew Keating from Internet2, and for a short introduction I'll pass the mic to Shelton Waggener to introduce him.
Thanks very much, everybody. We started working on cloud services a couple of years ago and presented at Reykjavik. And one of the biggest questions at the time was, if you start working with any of these cloud providers, aren't you going to be in a major vendor lock-in situation, worse than we are today, where your provider becomes a place where you put your data in and you can never get out? So we have been, within the US, we have been working not with one of the cloud providers, but many of them through the campuses. And we've brought together groups of campuses to really figure out a long-term strategy of pros and cons, knowing that it's going to keep changing over time. So Andrew Keating, who comes to us from UC Berkeley, has been part of the Internet2 team now for a couple of years. He heads up the infrastructure program for us with infrastructure, platform, and security services, and has led quite a few of these workshops. So he's going to lead you through the process that Internet2 is taking with our campuses in hopes that you would be able to learn from these and replicate some of them in your own NRENs. So Andrew.
Thank you, Shel.
Oh, you have your,
yeah.
Okay.
Great. So I just want to start out with a bit of an overview of Internet2's Net Plus program. I'll go fairly quickly through this because I think a lot of the data here and these slides may be familiar to many of you. So the Net Plus program in 2013, you can see the numbers of services that were available at that point in the different phases, right, that we had a year or so ago. 2014, we saw a tremendous amount of growth in terms of the number of services that were available through Net Plus. And so these are all categories of services: infrastructure services, software as a service, identity services, voice and video. We've seen tremendous amount of growth in the number of services through the Net Plus program over the past couple of years. The Net Plus program is actually only a couple of years old. And so this level of activity has really been happening most of all in the past 2 years. So within the Net Plus portfolio, we have a range of different categories for services. So we have identity and access management, we have infrastructure, platform, and security services, we have software as a service, voice video collaborations, and digital content for research and education. All of these services are underpinned through some core principles such as delivery via the R&E networks globally. They're built on federated identity and integration architecture standards. They're administered via global agreements. So we have global contracts with these providers. And so we're designing this service, these services in the different categories with these principles in mind. So in terms of the various portfolio categories and the number of services in each of these, just to give you an overview of what our members have been focusing on, in the area I work on infrastructure, platform, and security, we've seen a large number of services being developed, and this is the current status of services in the different areas. And so, as Shel said, we're going to focus mostly on the infrastructure, platform, and security services today, specifically on infrastructure and where we are. I just want to signal for everybody, if you're interested in other areas of the Net Plus services, there's more information on our website. You can reach out to us later. But for the rest of the talk today, I'm really going to focus in specifically on what our member institutions and what our community has been doing with regard to infrastructure services. So as many of you know, when you're talking about infrastructure as a service, the architectural implications are really around the hypervisor, right? So an infrastructure as a service provider is going to be dealing with anything at the hypervisor level and below. And the end user, whether that's a campus, whether that's a researcher, is going to be dealing with their applications, application servers, middleware, databases, operating system, anything hypervisor and above. Realize this is probably familiar to most of you, especially the technical folks, but I just wanted everyone to kind of have in mind the architectural implications that we're talking about when we're dealing with infrastructure as a service, because it's different from other areas of cloud services, right? So if we're talking about software as a service, we're really talking about the application layer only. If we're talking about platform as a service, it's different layers. And so what I think this chart kind of reminds us is that the blue areas are what we as infrastructure as a service consumers are responsible for. So we're responsible for our applications, our middleware, our operating systems, etc. And the infrastructure as a service provider is responsible for everything hypervisor and below. So that's the CPU, the networking, the storage, the backup, the data center, of course, the physical elements that allow that service to exist. So it's an important distinction to keep in mind as we talk through what the universities have been doing and thinking about with regard to infrastructure as a service. So from now, I want to shift gears a little bit, and I want to talk about the research dimension, because this is really what's been driving a lot of the infrastructure as a service developments that Internet2 has been working on. And so, we addressed some key questions, and we heard these questions from our member universities, from the researchers within those universities. And so I've just put up some of the questions here on the board, but, basically we wanted to know what sort of issues do researchers face in the cloud? What are the implications of doing a research project with a cloud infrastructure service instead of infrastructure or servers that might be owned locally? Then, our member universities were really concerned about, how can institutions, how can universities, how can research institutes help with cloud infrastructure adoption? So if they have a faculty member or a researcher that is interested in deploying a service or doing some research, what can the institution do to enable that? And then finally, thirdly, what role should R&E networks play in cloud infrastructure deployment and adoption? Should R&E networks be running the infrastructure? Should we be facilitating it? There are a number of different options here. And so I think these are key questions that have been informing the work that the Internet2 member community has been doing over the past couple of years. So how do we tackle these questions? We developed a series of workshops. So we brought together faculty, researchers, CIOs, and IT directors and IT leaders. We also brought together industry partners such as Microsoft, Rackspace, IBM, Intel, a number of other smaller startup companies. So we did a series of workshops. They were hosted at Internet2 member university campuses. You see some of the examples here, and I'm going to go into a little bit more detail on a few of these workshops in specific. So one of the first workshops we did was called Long Tail of Science. And this workshop specifically focused on social sciences. It was hosted at the University of Washington. University of Washington, University of Michigan were co-sponsors of the workshop. And what I want to highlight for all of you here is some of the key issues that emerged from this workshop discussion. It was a day and a half long, so obviously I'm not going to be able to recap all of it. There were a number of concrete projects that were developed out of this workshop where folks who came together said, we want to work on this together, we want to build an application, we want to do some sort of collaborative project across institutions, and in some cases across industry as well, because Microsoft had a strong presence at this workshop and was actually one of the industry co-sponsors of it. But some of the key issues that emerged from this conversation, and remember, these are social scientists, right? So these were economists, political scientists, folks whom we don't normally think of as being in the big data landscape, right? These folks were talking about, how they can analyze social data, and so things like Twitter feeds and things like economics data and things like that. So some of the key issues that emerged from this workshop were that they were very concerned about data preservation and permanence of data. What would happen to that data set after the research was done, after the paper was published. They were also very concerned about data data analytics and ensuring that they could have apps that could analyze their data sets, whether it was large or small or whatever it might contain. So they wanted to be sure that if they were storing data on a platform, that there would be the analytics there that could analyze that data. And then they were also concerned about the privacy and anonymity factors around research data. So when you're talking about economics data, for instance, that you could have personally identifiable information embedded in that, especially if you're talking about consumer buying habits or things like that. So there was an extensive discussion about how do we anonymize data? How do we deal with research data that's been anonymized, and then we have to use it again in order to verify the results of the research or to run the study again. And that turns out to be a kind of complex technical problem. So these are some of the key issues that emerged from this workshop. And I'm just going to go through a few of the other workshops to give you a sense of the kinds of discussions that were taking place. So we did a workshop that focused on genomics. This one was sponsored by the University of California, Davis. And some of the key issues that emerged, and again, from a day or 2 days worth of conversations, but around data storage and filtering of data. So if we're processing large amounts of genomics data, how are we going to store that longer term? The genomics folks were very concerned about human subjects issues. So, in the U.S. we have the concept of kind of doing, there's institutional review boards for any kind of research that's done using human subjects. And so what are the implications of that when it's our DNA and it's genomics data that's being stored? And so the privacy of personal health information was very important to these researchers because they're doing research on, in some ways, the most deeply personal information we have, which is our DNA. This group was also interested in enhancing analytics, and so understanding, what they could do to improve the sort of analytics that were available. Next workshop we did at the University of Hawaii was Earth, Ocean, Sky, and Space. And so this one focused on the physical sciences. And again, I hope you're all noticing a trend here in terms of the issues that were emerging, because once again, this group was concerned about, managing large and growing data sets. Now, the scale of data that the physical scientists were talking about was, of course, much larger because they have, telescopes and other sorts of instruments that are collecting vast amounts of data on an ongoing basis. And so storing it, managing it, and dealing with the growth of a data set was an issue that came out in this workshop that did not emerge from some of the others. They were also interested in data transfer optimization. So this is where, of course, R&E networks have historically played a very important role in ensuring that, data that's collected in one location, whether it's at a telescope array or something like that, is able to be transferred someplace else in the world for analysis and storage. And this group was also very concerned about data storage and preservation to ensure that the data would be accessible in the future for further analytics and research. So the final workshop I'm going to talk about was last August at the Argonne National Lab, and this one focused rather than on a specific domain of science, but instead on just the concept of how do we do open big clouds in general, whether it's for physics or astronomy or any other kind of research that might need it, genomics or whatnot. So we really talked about the convergence of high-performance computing with public clouds. We talked about moving large data sets, and so how does that transfer happen? Because most HPC work, you need to do it there on premise because the data set is so large that moving it someplace in the cloud just isn't feasible. Well, what are the limits and what are the boundaries of that? And so this workshop really focused on OpenStack for research. And this one, again, unlike some of the others, which were domain specific, was really focused on the technical underpinnings of what we do. So I think you all probably could tell there were common challenges that emerged across these different research domains and across these different workshops that took place over the past year and a half. There were technical, legal, business, and compliance issues that had to be addressed in order to enable fundamental research activities. And finally, we came to the conclusion, and our universities came to the conclusion, that R&E networks like Internet 2 can provide more than just connectivity. They can convene the community, as we did in the workshops, they can develop common issues, and they can collectively influence providers to tune the offerings for the research and education community. So I want to come back and just say a little bit more about the actual, how this is manifested in actual services that we have available through NetPlus. So these research workshops didn't take place in a vacuum. There were concrete outcomes that came out of each of those workshops in terms of specific projects. But more importantly than that, they actually gave us at Internet2 and a number of our member universities a sense of the strategic direction around how we needed to engage with infrastructure providers in particular. So to focus on the Internet2 NetPlus infrastructure programs, and you can see here some of our infrastructure providers, 6 of the major ones that we've been working with. We developed a set of core common elements that the universities really felt were essential, whether it was engaging with Microsoft for Azure or Amazon Web Services or Verizon Terramark or AT&T or Rackspace or any of them. Those common elements were, of course, network peering optimization. We want all of these infrastructure providers to be directly connected to the research and education network for improved performance. We also, from a business standpoint, we want a commitment from the providers to best pricing and to best business terms. Because what we heard loud and clear from the researchers at these workshops was that they don't want to have to negotiate pricing with one of these providers for storage or for compute. They just want to know that their university, their institution, is providing them with access to the best pricing, whatever it is, and then they can develop a grant budget or proposal or what they need to do. So having that commitment in place contractually with the providers is incredibly important to researchers. Researchers also told us that they really wanted a data egress waiver, that they didn't want to have to worry about charges to move their data around into or out of any of these providers. So we have that in place with Microsoft for Azure. We have that in place with Amazon for Amazon Web Services. And with some of the other providers that we're working with at earlier stages, it's a premise that our universities begin with when they talk with the provider to say, if we're going to develop a program at scale for cloud infrastructure, you have to agree to waive data egress. You have to agree that our data goes in and out as we need for research. We also feel it's important to have customized contracts and legal agreements. So the university said very clearly that click-through terms that many of these providers offer just aren't tuned to the needs of researchers or to higher education. So we have groups of universities that work with the providers and bring their lawyers to the table to actually help the providers draft agreements that will work for the research and education community. Everyone has also said that these services need federated identity integration, right? So we need to be able to authenticate, log into services, access services, even if it's a management console or depending on the type of services, what that looks like is going to vary, and that has to be tuned. But the core principle is that there has to be federated identity integration. Data preservation and portability is incredibly important as well. It came through loud and clear in the research workshops that almost every group of researchers was interested in what was going to happen to their data set on an ongoing basis. And so when you're talking about storing it in an infrastructure provider, that means ensuring that there is reliable infrastructure in place, also ensuring that the provider has business continuity plans in case they get bought, they go out of business, there's some kind of disaster. So this idea of data preservation is something that happens at the individual research project level, but it also needs to be thought of at a higher level when we're engaging with infrastructure providers. Similarly with data portability, researchers wanted to know that if they store their data set in one provider, but then they decide for whatever reason 5 years later to move to another provider, that they're not going to be locked into any kind of proprietary format, because most of them are researching and collecting data in using open formats and open standards. Privacy, security, and compliance are incredibly important as well, and you heard this from the genomics discussion, but certainly all the domains of researchers were interested in ensuring that data could be anonymized. Researchers want to behave responsibly and treat their human subjects data responsibly, but then their data set as a whole needs to be kept secure, needs to be kept compliant, whether it's with law or with policy, and that has to be a part of all of the discussions with the providers. And finally, the researchers told us and the universities told us that it was very important that each of these providers has a commitment to research and teaching collaboration. So going through a number of those workshops, we had co-sponsorship from Microsoft, from Rackspace, from some of these leading industry players who really wanted to work with us and wanted to work with our community. So it really is about not just selling a service to us, whether it's infrastructure or something else, it's actually about working together to improve the service, to ensure that it's optimized, to continue to have these kind of workshops and develop them further. So these are the core principles that we've developed as part of the Internet to Net Plus infrastructure programs. Many of them actually carry over to other areas of Internet to Net Plus services, but I wanted to highlight these that were specifically relevant to the infrastructure area. And just to give you some details fairly quickly on a few of the services and the different stages that they're at. So Microsoft Azure, we've had for about a year now available and open to universities. The participation is open to all education and research institutions. We just updated the legal agreements. We do ongoing work to ensure that those agreements are tuned to the needs of researchers and of campuses. And we do have the data egress. So this is one program that's available. We've seen a number of Internet to member universities move to Azure and move to the cloud, both for research and then also for the IT operational side of campus. And I should say at this point that, of course, there's a lot of carryover to what IT operations does and needs in terms of cloud infrastructure. But my focus today has been primarily on the research side. But of course, a lot of what we've been talking about is relevant to IT operations as well. So the Amazon Web Services program is one where we had the University of Virginia sponsoring this effort. We've been working on it with the University of Virginia and 5 or 6 other universities for the better part of a year. We've actually worked pretty intensively on the legal agreement and the contract. We have a program in place for network peering. We have a program to waive the data egress charges. And so our next step here, really, the universities have put in a year's worth of work, and we're really at the launching point now where we can actually have some universities begin to sign up, Internet to member universities begin to sign up and actually start moving their researchers and their AWS accounts into this program. So this one, in terms of the phases, is actually just finishing the service validation phase. Microsoft Azure that I showed you a minute ago is actually in the early adopter and general availability phase. So another service that's just starting the service validation phase is with Rackspace around ownCloud, Openstack, and we have university testing that's underway. We have some research projects that are underway already. So we've already begun integrating with the Internet 2 network, but we're still evaluating some of these other areas, and the campuses are still determining what the identity integration looks like, what the business model and what the legal model is going to be. So this one is just at the service validation phase. So to wrap up, just a few conclusions and lessons learned from a couple of years' worth of work with our campuses and our researchers on cloud infrastructure. So one important lesson learned is that researchers and institutions face significant challenges with cloud infrastructure. And I think everyone could have expected this, but if you think back to the architecture slide that I showed you earlier on in the talk, the challenges don't end at the hypervisor layer, right? The researchers and the institutions are concerned about the physical security of the premises. So even if they're buying infrastructure, they want to know what's going on at the hypervisor layer and below. So the architectural implications when we're thinking about a cloud infrastructure service only get us so far. We're actually thinking about the full stack. So legal, policy, and business issues must be considered alongside technical and architectural considerations. It's not sufficient simply to plug an infrastructure provider into an R&E network and expect researchers to get the benefit that they need. We have to deal with the contract issues, we have to deal with compliance issues, we have to deal with data handling, we have to deal with a whole host of other issues as well. And so finally, we've seen from our member universities that community-developed solutions offer a way forward, but that they require a significant and sustained and consistent commitment from all stakeholders involved. So some of these projects for validating services have taken 6 months, some of them have taken a year. That requires a commitment on the part of the provider, it requires a commitment on the part of researchers and of the campuses, and frankly, it requires a commitment on the part of Internet 2 and any R&E network that is wanting to work on developing one of these programs. And with that, I will wrap up. But just to let you know, I hope we have some time for questions and discussions at the end of the other talks. But if you want to reach out to us, you can find us Internet2 on the web, of course. You can email us at netplus@internet2.edu, or feel free to contact me directly.
Thank you very much for the presentation, and please stay here. I'm just wondering whether we have questions.
Oh.
Now we can ask.
You can do questions now, or do you want to?
Yeah, we can do questions now.
Sure.
I think we still have time. So questions either to Andrew or to Shell. Yeah.
Yep.
Ahmed Dabbagh from Ankabut, the United Arab Emirates Enron. I think it's very important what you have said here about the cloud and Net Plus deployment. I think we worked with Shell from 1 year about the global Net Plus. One thing it hurts my attention here, which I need a confirmation from Internet2 about it. Public cloud, they are everywhere, except in our region, unfortunately. Which means the usage of the network for the NRAN is mandatory to deploy the service to our members. Correct? Is it mandatory for you when you are negotiating with the vendor that this service has to be peered?
Yes, absolutely.
This is the first commitment from them. Okay,
Right.
Now the question to the vendors, I'm asking why you are doing this in United States and in Europe. When you are coming to our region, you are refusing to peer with us. Thank you.
Yeah. No, I think it's important, and I think it's something that Internet2 would like to work with you and the other NRENs on, because we view this as a global sort of thing. And Shell, do you want to?
There's a session tomorrow in the afternoon giving you an update on some of the global projects that are going on. And one of the key issues is how do we as NRENs and research and education in general coordinate to the benefit of the providers so that we aren't, we aren't the easiest to do business with. I know that'll come as a shock to some of you, but the providers want to work with us in a consistent way. Yet for many of the providers, when we go to do that globally, they're not coordinated at all. So you'll get one answer to Janet, and another to Switch, and another to Ankabut, and another to RMP, and another to Internet2, because within that entity, they don't raise those issues up high enough. One of the things that we require in our program is an executive sponsor at the senior level outside of sales with the provider so that we can get those things done. Because the sales organizations have no incentive to do anything common globally, because that's not where they get their commissions. They get their commissions locally within your region. So it's very easy for them to be incented to keep that differentiation in place. And that's something that we as a community have to figure out how to help them solve.
So, any other quick question? We're going to take one more question, if we have one. If we don't have more question, I'd like to move to us. Thank you very much.
Thanks.
So, you heard an approach which is basically to make close partnership with commercial cloud providers, and the next two speakers will illustrate another approach, a different approach, I believe. The first speaker we have is David Jericho from AARNet. Let's go ahead.
Good afternoon. As you can see, that's a rather long title. With respect to all the things that Andrew said, that's something that worries us in Australia too. And we've got questions about international data provenance as well. So my colleague Guido for years was hassling me about, can we create a cloud solution, cloud storage, give me something. Anyway, one afternoon, Friday, I'm drinking beer, a bit bored at work. Finally get to doing it. This is what we ended up sort of coming up with and proposing after a little bit too much beer, maybe. The intent was, and as you can see, Australia is surrounded by lots of water. I think the Pacific is 160 milliseconds east. Singapore is 80 to 100 north. And Australia, as you can see there, from the top left to the bottom right, other way around, top right to bottom left, is an 8,800 kilometre network path. And yet you've got huge sensor networks up in the top right and supercomputers in the bottom left. So this is kind of what we were thinking about doing, something vaguely like that, distributing data around the place, multi-master active, clustered, so on. Where there were places, for example, in the middle of Australia, or even just north of Perth, where there weren't that many users and potentially not that much data, sort of thinking we'll put a cache in or something. This is what it's ended up looking like. It looks like a significantly smaller thing, but the interesting thing is we aimed big and we, funnily enough, succeeded relatively small. Of the two combined cloud storage services on one of them is FileSender, which some of you are aware of, and the other one is ownCloud. We've seen roughly 12,500 logins. Most of those are researchers. On average, within our cloud storage, we've got roughly 3 gigabytes per user, which doesn't sound like much, but it really is the Pareto principle in play here. 20% of our users are 80% of the bulk storage, both in file count and bulk storage. Word of mouth, funnily enough, and this is an experience I've had most recently with my sister, funnily enough, starting as a communications officer at the Monash University. And word of mouth advertising was the very best advertising we could get for this entire thing. No matter how many times we said to IT directors and IT staff and so on, we've got this thing out here, go use it, go use it. They forgot to tell the end users. And no matter how important IT staff think they are, they're not the biggest department. And one of the other things that we worked very, very hard on doing was making sure that at every user, at least the majority of users, I should say, who are using the service, will get at least 300 megabits a second for their sync and upload clients. And that's actually surprisingly hard to do when you've got people still using Windows XP laptops behind university firewalls and your server is 800 kilometers away. It's surprisingly difficult. Future intentions for this, we still want to make all the data user proximal. As I said before, we're a long way from everybody else, but the internet has made the world a very, very small place. One of the key drivers for our initial project being FileSender was we had a geology researcher in Melbourne who wanted to get data to Switzerland. Part of the work has been done is one of the things we want to do is per user and per realm defined replication rules, because we still have the data provenance thing. We don't want all data replicated everywhere, so it makes sense for users to be able to tag whether this can or can't leave the country. That's an intention. NREN partnerships, we've worked with some people just to do some experiments and so on. And that's obviously the way to go in the future. I'm not convinced about going to people like Amazon or Rackspace. They don't understand what it means to actually push data into something at 300 or a gigabit a second. And the interesting thing is that actually makes it fairly easy to quantify the value of the service. The other thing we want to do is we want to put caches or access nodes on university sites so that we can bypass firewalls and so on, actually get wire speed at 1 millisecond or less. And as I note, and anyone who attended the EduPert workshop, TCP is a problem. So what did we learn first in this particular exercise? We initially set out using a commercially supported version of Hadoop. We went that way because it had a solid, fast NFS server. The tin that the product came in said we do distributed transatlantic multi-master replication and so on. And it provided a solid, fast NFS server because everybody still talks file systems. The curious thing we found, and even though we experimented with this in the lab, the incoming data would exceed the rate it was being replicated by an order of magnitude. The whole stack, that this entire Hadoop implementation would come screaming down in a heap, deadlock errors everywhere, two competing things arguing with each other about who had what, and it would never recover. To the point where I would actually have to physically hard boot the boxes using the reset button. Of note, still a good product. I haven't mentioned the name. I'd still use it elsewhere. It just wasn't suited to our network environment and use case. In some searching, we found ExtremeFS. Some of you may have heard of this because I believe it came out of Germany. Ticked all the boxes in a pre-evaluation. Sat down, did an evaluation, you know, the usual sort of things. The file system driver had written on Fuse, a bit rough around the edges, but we still persisted with it. And we ended up writing our own policy handler to manage the concept of quorum replication, because the way it did accepting of a file, it was easier to make sure to try to write to a local replica than replicate out. But unfortunately, we came across too many crashes, unexplained things, and as we continued to find, network latency and data rates would continue to be a problem. Once again, convincing product, don't have anything bad to say about it otherwise, just not suited to our environment. We were a Red Hat shop. We routinely meet with Red Hat because they love to brag about the fact that AARNet's a Red Hat site. So we tested Gluster FS because I've had many arguments with their support engineers about this, and they insisted that it could do it. Same as the previous two products. Both suffered under latency. File system and replication interfaces got in the way of throughput. And funnily enough, CPU utilization was the highest of all the things I tried. And even things like the OSD brick matching within Gluster became very problematic. Given that this is a cloud solution, we're trying to design with cloud methodologies under the assumption that hardware and software fails, and the brick thing became a real problem. And curiously enough, I mean, it wasn't a blocker at this point, but given where we want to go, it's not an object store. We tried Ceph. We have 700 petabytes of storage for NetFlow and other data. Doesn't really work that well over high latencies. Sydney to Canberra, which is only 4.4 milliseconds. The maximum I could write into a Ceph cluster was about 200 megabits a second aggregate. We examined a few others in the lab. None worked. Tried all sorts of things, putting feelers out everywhere, didn't find anything. In desperation, this was kind of funny, maybe it was beer-induced again, we tried BT Sync from BitTorrent. And I know many people who even work on ownCloud and otherwise use this personally, little Raspberry Pi sitting somewhere. Just didn't quite work. So at this point, we're out of distributed POSIX-like file systems. And what we ended up falling back to was an active-passive setup. One thing we are able to do in our environment is, because we understand the network very, very well, we're able to control the TCP behavior between all our nodes. We do replication as an active-passive mode at most a 5-minute delta, as I've noted. And the metadata for all the systems and all the files is in a distributed quorum-based database. HA Proxy, I love this product, does all the heavy lifting. A lot of data on a lot of information on the Faster Data website from Energy Sciences, but it works reliably. We tried all sorts of other things. We considered pulling back the storage to put it all in one place, but just didn't quite see the point. And most importantly, the users don't notice. If we need a proxy in a hurry, and funnily enough, one of the proxies on my chart that I showed was exactly this. I spun it up in a hurry. One of the other things we learned, Linux's TC, the little traffic classifier tool within the Linux kernel, just did not work to generate what we were actually seeing in the real world. We've got some old Cisco 7600 chassis that we use in router mode. We were actually hitting network buffer issues on the line cards, and the TCAM was having issues as well. The net result was throughput for any given client would drop from, keep in mind we were aiming for gigabits a second, throughput would drop down to under 100 megabits a second, even though the link was 90% idle. It was just the weird confluence of behaviors of distance, TCP, and the router mode, and the line cards in question, that would result in this. In order to work around this, because we couldn't actually do this in a lab, we found a little bit of budget and went and bought some pre-production machines, or pre-production staging solutions, and put them beside the particular environment. Didn't have to be identical. Close enough is good enough. Curiously enough, I had 2 hardware failures just out of the blue, which was quite fascinating. We just put a stall on that. This was one of the interesting discoveries. In our particular case, given that the network was quite busy and the 7600s had been established as a cause of a large part of our problem, and as I note, if we can't do it faster than everybody else, why would they bother? I mean, compared to many other products, things like ownCloud and FileSender are actually very, very basic. We turned off explicit congestion notification on our routers instantly, a doubling of throughput. A little bit network unfriendly, but I'm a sysadmin, I don't care. But interestingly enough, the sawtoothing that we got with TCP was greater. The average throughput was higher in a particular test environment, but when you had, once again, a Windows XP laptop, it actually had a very negative effect. So I applied a sledgehammer, and I I don't know who here has seen Office Space, the movie, but the boss, Bill Lumbergh, when he stands there with a coffee cup and he's about to ask his employees to work on the weekend. And every time I see this, yeah, I think of him going, yeah. Very uncomfortable, because the behavior that this actually does to the net links out of these 7600s, I will get 10 gigabits a second out of a busy interface, but it is unfriendly, sometimes 6,000 to 7,000 retransmits at a time. But that said, everybody else on the same particular shared routers is, well, the CDN services and the like, they're actually very small, and the way things are working, they're not being negatively affected. It's just the way I have to brute force this particular problem. We're working on fixing it, but as is all things, it's not always immediate. So what did work well then? This was the big surprise. We've got metadata floating around with the files and so on. I'm using MariaDB with Galera. I honestly expected this thing to fall down in a screaming heap every 5 minutes. So far, it has been the single most reliable element of the entire cluster. We have National Quorum, but because it's a Paxos algorithm, it's not that expensive. It's always the closest node that answers. So by putting out more replicas and increasing the quorum somewhat, and wisely choosing where the query originates, it's not a problem. Read benchmarking, it is as fast as running the database locally on SSD, which is where the databases live anyway, but the distance, the 65 milliseconds between nodes, makes no difference. The ownCloud write-into rates, as I note, aren't limited by the quorum decisions. It's very, very quick. This is probably the only downside of it in all up, is that a human decision is required to choose the node to bootstrap from. But that said, 280 days of uptime without problem across the cluster, 3 terabytes of insert and update, which in a file sender in an ownCloud world is a reasonable amount of data, not had a problem. But one of the curious things with going this particular approach is that you do need to modify the tables that are in use. And this actually stung us very early on. Thankfully, no data loss. But you need to have primary keys. And as I note and where I'm leading to, one of the things is that in that particular model, we are operating with no SQL assumptions. Apache HTTP. People love to rubbish Apache as being slow. Funnily enough, turn off your HT access, you'll double the performance overnight. And this can apply to almost anything. But one of the neat things about it was also using the pre-fork handler. We were able to trivially calculate capacity going forward. I can say we will handle 300 users on this server. We get to 600 users, we need double the servers. Simple standard PHP tunings work just fine. We didn't really have a problem with PHP. The tools in question aren't the fastest out there. PHP isn't a superstar when it comes to computing data, but it worked just fine. HA proxy, as I said, I love it. The SSL termination works well, 3 gigabits a second per core on the $300 Xeon processors we're using. And one of our intents in the future, as you know, is to use Speedy to try and speed things up. Simple SAML PHP, worked just fine. Proxies and caches. This is a standard CDN trick, nothing magic, but it's amazing how little information there is out there on this particular topic. But what it allows us to do in a country that's 8,800 kilometers wide by the network path is bring the content closer. And to some degree too, it's always cheaper than taking a full copy. 7,200, 200 disks in a chassis is really quite expensive compared to 1.5 terabytes of RAM in a server. And if you have to reboot it, who cares? You'll just transfer over the network again. I think I repeated that title. Whoops. The things we really did learn. Distributed multi-master is really, really hard. You can stand here and go, duh. But we're still working on it. We haven't given up. But it will rely on certain other assumptions in the way we operate. Network performance is still a problem for end users. We all know this, of course. But curiously enough, if you can do 100 megabits a second, you have users talking about how fast your service is. 300 megabits a second, they rave. It's the most amazing thing. But that said, I sit there and I watch 300 megabits a second from my desktop to a server and I complain about it being slow. And I spend the rest of the day digging into why it's slow. Funnily enough, experimenting with the software, the flavor of the day, everybody likes to go out and play with a new thing. Don't bother. Don't go chasing Nginx and fast CGI to do this, because it doesn't really matter. The users aren't hitting your service that fast. It's not supercomputing. It's not big data. It's not any of the buzzwords of the day. The other thing we learned, obviously, data loss is the single biggest sin. Doesn't matter what else you do, your service can go down. If you lose data, you're in trouble. Because users aren't backing up their data. Part 2, users use the service without thinking about it. And this is actually one of the key things I think we aimed for. And then they complain quite ferociously when it fails. You ring them up, and some of the tickets I've seen that come into the system go, oh. But then the moment you fix it, gushing praise. And they love to rubbish the competition. You know, name drop whoever you like, they sit there and rubbish the competition. It's almost good fun. One of the other problems was, and this is a software problem, we have to stop thinking about files as files. They're objects. I mean, what's a file system other than a database with a set of metadata? So it does complicate the problem massively, though, because there's a great deal of attributes and so on that we don't care about. Most users never get anywhere near our quota. As I noted, 3 gig, we provide a 100 gig quota for all our users. Most are at 3. Oh, that's an average, I should say. And this is a curious feature of ownCloud. It doesn't matter how fast or close you are to the server, 2 files a second. If you have a 10 gig interface out of your desktop into a server and you can zap a gig a second across the wire, you will do 2 gigabytes a second. Well, I shouldn't say that actually. You will do 2 objects a second filling that wire at 10 gigabits a second. That's what I've found. You're on the end of an ADSL line and you're transmitting 10 kilobyte files, it'll be 2 files a second. Where are we aiming to go now with this? One of the things, and this is a bit of a learning, no more big chassis. We went out and found 72 disk Supermicro chassis, great big heavy things, 110 kilos a piece. But this is a problem, a genuine problem that we're struggling with at the moment with another project as well. We can't get these into data centers. Nobody will take them. They're 1 meter 10 deep, 110 kilos. The power supplies on the back say 6 kilowatts in total. Nobody wants them. And of course, risks of large points of failure. Anyone who designs a cluster storage knows this, of course, but you know, with the model we went with originally, it wasn't necessarily going to be a problem. Rebuild periods can become a problem as well, load intensive. We all know that for anyone who's run a cloud storage, a cloud file system. Although the density is very tempting. There's a solution from our Supermicro vendor that I can put 5.4 petabytes in a rack. Oh, and as I note as well, 4.3 petabytes on a single 15 amp rack, a circuit. But this is where we're probably going. The data rates aren't that high. So we can probably go an Atom system, low power, 20 watts a piece, throw on some disk, 80 watts. And continuing to stick with AARNet's design mantra of divide and conquer. It's something that we've done for 10, 15 years now, and we need to continue doing, and this is a classic case. One of the experiments we're running at the moment, and it's related to another project I'm working on, using SSD content caches to provide that distributed model, but instead of putting data everywhere, put it in a few places and then cache it. Object stores. I was actually really hoping to have a demo that I could show off, but I never got around to it. Never finished it, unfortunately. But Apache Cassandra, working on data models just to throw data in there. And I've been somewhat inspired by Adrian Cockcroft's performance work from Netflix on this very topic. The other solution is OpenStack Swift. They swear black and blue that it will do what we need it to do. It's worth a test. And once again, I can't stress this enough, and this is something that we're trying to work on internally. They're objects. Let's stop talking about them as files. They're not file systems. Nobody cares. And then as well, the metadata should live in the same system, and that's actually one of the risks we run at the moment with the fact that we've got a 5-minute delta. Most of them handle it pretty well, but that's a data loss risk. But as a note, it will require large rewrites of code and rethinking the data models. It was surprisingly hard to write a proper file storage model for FileSender in Cassandra. And that's the things we learned.
Thank you very much. So at this point, please hold your questions. I suggest to move quickly to the next speaker. So we have Jakub Moscicki from CERN with us, and he will again present the use case, something that they built on top of ownCloud, and after that we'll have chance to put questions to the two speakers. So please.
Good afternoon. Can you hear me? Yep. Good afternoon. My name is Jakub Moscicki. I am a service manager in the data storage services group at CERN, and I will tell you today a bit about the idea of CERNbox service, the deployment experience we had so far, and the status. So, what we do in the ITDSS data storage services group is provide data storage services to back the science we do at CERN. So we're talking about doing physics. Okay, we have a wide range of different services that cover a whole spectrum of parameters like concurrency of access to data versus latency, how quickly you access the data, number of files, and the sizes. So we have different systems to cover the entire spectrum. So here I put three main ones. So we have AFS, which is the general purpose file system. Currently we have 2.5 billion files in this system. It represents 300 terabytes on disk. And we have around 3 million reads and writes per day. It sits on 300 disk drives, implemented in a classic RAID model. We have, for the physics data, we have a low latency physics storage based on disk called EOS. It has a super fast namespace, so we're talking about tens of kilohertz of file stats. Scalable I/O. It represents currently around 50 petabytes on disk. We have around 30,000 disk drives, and this system implements a RAIN model. So a file replicas are not distributed across the disks in the same node, but they're distributed across different nodes. And finally, we have Castor, which is archival and bulk data storage on tape. So why we started thinking about CERNbox? Because we think that we have a missing link somewhere. We see a trend of users at CERN increasingly relying on external storage providers to store their files and to store their data. Sorry. Okay. So what we are missing is easy access, kind of cloud storage access for end users. Okay. So files that go automatically to the cloud and are available always and everywhere. So this is very useful. So for example, a broken laptop does not necessarily mean that you lose the data, right? Because it sits somewhere in the cloud. Offline access to data, so work on the plane and resync when you're back online. And this is much more frequent than one thinks because we also have people working in the field and across the campus. Keep files in sync across different devices and specifically access on mobile devices. Sharing files with colleagues, which is still surprisingly difficult in organizations, especially if you have different operating systems and different file systems. So can we have all these added features for documents? So small files, PPTs, texts, typical things like you would have in Dropbox, and for science data. So integrate it into the data processing workflows and existing infrastructure that supports scientific research. So we have a CERNbox beta service to address the classical Dropbox use case. Okay, so why people use Dropbox? Because it's a no-brainer, okay? It just works. You don't have to do anything. You just install it, and then it works and syncs your files, and the files are available everywhere and always, and you don't have to think about it, okay? And it works on all devices that you're interested in. It gives you a consistent user experience across all these different devices, okay? On Windows, on Mac, on Linux, and on mobile. So this platform integration aspect and ease of use is a key factor here for the user uptake. So this is how we deployed the beta version of our service. So the setup is 100% Red Hat 6 on standard hardware. So this is also a redundant setup, so we have a guaranteed failover, and we did it by the book. So you have Apache load balancer here, application backend servers here with PHP 5.4. You have MySQL server with sizable RAM, and you have NFS servers in async mode, and JBots with rated. Okay. So what has been the usage? So we have started this beta service in March, so we are in the 3rd month of beta. Okay, and you can see that we have a usage growth. So every month we get around 90 users more. Okay. Interestingly enough, when we started in March, we already had 190 users that we inherited from the initial prototype deployment. So this is interesting. This also shows you how users are eager to use something like that when it shows up in your organization, when it's available in your organization. So even before you start thinking that you would deploy something like that, you already have users. In terms of file sizes, so we have 700,000 files added every month. And the size also grows accordingly, so around 500 gigabytes added every month. So if you analyze what's the size of files that users keep, so what's the total size of what users have in their repository, majority of the users, they have less than 10 gigabytes. Okay? Some 15% of the users have more than 10 gigabytes, and we have few individuals that have up to 100 gigabytes of data. For the files, most of the people have less than 5,000 files in this system. And 5%, they have up to 20,000 files. And again, few individuals who put in the order of 100,000 files. So some user feedback. So it's been very positive so far. So here are some quotes, not all, some quotes I choose. It's interesting. So people would say, oh, I ran out of space on Dropbox. I want to have more. We offer 100 gigs. Okay, this is one motivation. They also appreciate having mobile access. Some people are just very happy. Okay, we also see some problems with battery draining on the clients and so on. There's also an interesting point here is that people, apparently many people, they do have their own cloud server at home on their NAS. So some people would like to integrate these two. Okay, now we also see, so we have this feedback, surprisingly positive, but we also see many idle accounts. So maybe this feedback survey is skewed by the 5% of enthusiastic users. I don't know. So what about the file access patterns? So for every file that you put in the system, you download it twice. Okay, so the get to put ratio is 2:1. If you look in the file type distribution, so we have 1,200 different file extensions there. So this is certainly not just Office type of files. Surprisingly, 30% of this is C code. Okay, non-surprisingly, you have lots of images. 15% there's no extension, so basically this tells you that people are from the Unix world typically would use it. Okay, and also 25% is the rest. So typical stuff you would expect, like PDFs, text, PPTs, and so on, but also some stuff that is specific for analysis, like data files, which are in this format, Python scripts, EPSs, whatever. In terms of how people use sharing functionality, you see that the number of shares is more or less corresponds more or less to the number of users. Okay, so this is what you expect. In terms of request frequency, so if you analyze what's the frequency of different requests on your service from all these users, so if you consider file operations, put and get, and metadata operations, so checking for updates, you would see that basically our system operates at 4 Hertz all the time. So basically it's idle all the time. And you have spikes of activity every now and then whenever people are uploading something. So it's quiet, and then there's a burst. It's quiet, there's a burst. If you take out the metadata operations, then you consider only puts and gets of files, you see that it's even less. So the mean value here is one file uploaded or downloaded every 3 seconds. So there's lots of cold data. So we've been also testing ownCloud in the lab, and our tests have been partially automated and are available on GitHub. And okay, important things for us are issues with the client. So the change detection is not ideal. So you have full scans of local and remote folders that take a long time and drain battery. The client behavior may be confusing if the file system is modified while it's syncing. The file conflict resolution, yes, it's implemented, it works, but directory conflict resolution, no. So if you have one client adding files to a directory and another client deleting that directory, you will end up in a mess. CERN are cases of illegitimate file deletions. Don't use symlinks. Never have a file, two files that are only different by a case of the letters. You may run into trouble. Okay. We also found that file versioning and trash bin are a must in this kind of system because there are always conflict situations which may only be resolved manually by the user. So you always have to give a possibility for a user to go and manually recover the version of a file. Okay. So we have this currently deployed CERNbox beta service. So works okay so far for the classical Dropbox use case. Low frequency document sync and share. Now, can we bring the system to the next level? So can we have our core business workflows and large-scale workloads? Can we add this capability to these workloads? Can we expose all of our existing data from day one? Can we integrate into physics data processing ecosystem? And can we sync higher data volumes at higher rates? So can we add this easy of use Dropbox-like access and integrate it into the scientific research environment? And can we still keep the simplicity of it? So let's consider the current architecture. So you have typically sync client talking web dev and the web access over HTTPS. They both go to the load balancer. Then there's a number of backend servers, and the metadata would be kept in a database, and the data would be kept in the storage. So there are several problems with this. So first of all, the database keeps track of sync state for every file in the system. Okay, so that would essentially mean that as you scale up the storage, your database would explode. One thing. The other thing, it gives you all sorts of interesting problems when the metadata gets out of sync with the data. And for a synchronization system, it's pretty important not to run into this situation. Another big problem is that current interfaces to storage are via file system. So this is not a good idea. This doesn't scale. This is what we put and get are objects, just like David said before. It's not files. This is just inefficient. Okay. And then still on the database side, currently in the implementation, there are huge SQL overheads. So essentially, this is the limiting factor in the terms of number of operations per second you can do. This is why you can only do 2 ops per second. This is why on your ultra-fast network, you can only put 2 objects per second, because then it goes and spends lots of time in this database handling here. And files that we put here are all put with the credentials of some admin account, and they are not directly exposed to the user. So they are only available via web access or the sync client. So we've been thinking about how to improve that situation, and this is our revised architecture. So we still have WebDAV sync clients and web access talking to the HTTP load balancers, but then what we do is we separate the web traffic from the data traffic. Okay? The data traffic, the sync traffic is really on the critical path. So the web traffic goes via the ownCloud server here, whereas the web traffic goes, the sync clients are talking directly via the proxy directly to the storage, to our storage system. Okay, what do we get with that? So all sync state is kept as metadata in the storage. Okay, so we keep metadata where data is. And actually we did it in a way that we don't even have to have any extra metadata attributes. One thing. The second thing is this system works in the following way. Consider the upload of a file here. What will happen is that you will internally get redirected to one of the disk servers. Okay? So the system is composed of a namespace, very fast namespace, and replicated disk servers. If you consider a file upload, you would be redirected to a disk server, and then you'll be just talking to this server. So we have split the data flow from the metadata flow completely. The metadata, we can do very, very fast metadata at the kilohertz rates, just talking directly to the namespace. And we consider here we have two kinds of redirects here. We have internal redirects. So thing that is hidden from the redirect, which is hidden from the user. So you ask for a file, and you are redirected to the disk server that has it, and it's served via the proxy, or an external redirect. Okay, you ask for a file, so a client asks for a file, and it's redirected on the client and talks directly to the file server. We have two kinds of redirects in this system. Then we have files which are written with user credentials. This means that data is directly accessible by the user via other means. So what we get with all this? We get immediate access to all our data. We simply add a sync and share capability on top of existing storage. And of course, you would not sync petabytes of data to your laptop, but this opens up for a whole new world of possibilities, because we have all files, all interesting files already in the system for LHC experiments plus all the public data. And the interesting number here is that for 64 petabytes of data, we have around 30,000 hard drives in the system. Okay, so by doing this, can we achieve massive scaling at reduced cost? Well, we don't need to keep track of all files and directories in the database, and we can avoid explosive growth of this database infrastructure. So what's our file number estimate? Okay, we have a system. With 10,000 users on AFS, we have 2.5 billion files. We know that in some time, we'll have to handle this kind of number. Okay, what's your number for 100,000 users? I don't know, but think about it. So before we start throwing hardware at the problem, consider the cost of running the service. Okay, there are fixed costs, but also scaling costs. If you really want to scale it up, then you will also scale up the number of hardware incidents, the user support, the backup, integrity checks, upgrades, and all this. If we can use it, if we can already use existing infrastructure to do this on top of an existing system, this is a big gain. We don't have to pay for all that. We already have that. So for massive scaling, we really need to keep the total cost of ownership under control. So profit from existing large-scale operations and support of our storage services, and really exploit economies of scale. And we have regular discussions on scaling issues of this kind of system with several partners. And one interesting example here from CNRS, they calculated how many database servers they would need for 100,000 users just deploying ownCloud with the old in the regular architecture. So this is a link, you can read it. It's in French, but the numbers should be easy to get. So once we get the system, what can we do? We already have a storage ecosystem for scientific research. So we have this large-scale storage, and we have batch farms which are accessing these files, just copying in and out. We have analysis cluster, which use high-performance protocol, and applications that are using this high-performance protocol to access the data. Okay, we have also users that are able to use online file system access to the same data storage. So what we do here, we add sync and share and offline capability. We add to this ecosystem. So where we are with this revised architecture, so we are at the advanced prototyping stage. So essentially what we did, we adapted existing WebDAV interfaces in our storage system to be compatible with ownCloud sync clients. And we have been testing this in the pre-production environment, which runs on standard hardware. The namespace node, so in EOS, runs on this hardware, so also pretty cheap hardware. There are around 50 disk servers, so there are cheap JBods with 1,000 disks in total. One important thing to get here is that we use the storage layout with 2 replicas in the rain mode. So it means that for every file put, we store it twice on 2 different file servers. Okay, so this is also important to understand. We can very easily reconfigure these parameters here. And the underlying storage scalability for the EOS production system is such that it should never be a bottleneck for us, for our system. So you really have gigabytes per second of throughput and tens of thousands of kilohertz of stat rates. So some performance numbers. So consider a scenario where you sync lots of small files to a laptop in a campus over the Wi-Fi. With the ownCloud client, we can currently get like 30 hertz downloads and 50 hertz uploads. Another scenario, if you sync big files on a fixed gigabit network, basically you have like 20 megs uploads per second, and downloads is basically in a gigabit per second. So this is with internal redirects. With external redirects, your sync client for data access is talking then to whatever the number of file servers you have. Okay, if you have 100 file servers, it will go and talk to 100 file servers if you do 100 parallel requests. All right? So then basically you go as fast as your network goes. Module of the latency. Okay, some more performance numbers. So we've been also testing a little bit about with very simple test program based on PyCurl, so not a great performer. Okay, with SSL sessions. So we've been testing how quickly can we stat files, so the metadata access. So prop find with this simple PyCurl test program. If you ask for 1 file entry at the time, you do a full round trip, okay, you get 90 hertz in our. So this is listing 1 file at a time. If you have a directory with 1,000 files, so you do ls minus l, that directory, you get 1,000 files in one response, okay? And then you go to 8.5 kilohertz immediately. So you can basically list 8.5 thousand files a second. And if you have a super huge directory with 10,000 entries, you're also staying in that zone. Okay. For the small files, which is a really killer in the current ownCloud architecture. So if we do a PyCurl sequential download of files, we are at 30 hertz. And then we start adding threads to it, and we are simply scaling this up. So basically, the server is not a bottleneck. You can go as high as you want, essentially. So here, it's like we get 120 hertz, no problem. Same for the uploads. And the deletes are also very, very fast. So basically sequentially, you are talking about 60 hertz of deletes. Oh, yeah. And we also tested this with ownCloud Sync Client, and here you can get as much as 50 hertz of uploads. Okay, so this is just a summary. Sorry for running out of time. So we have a beta service for document sharing. So it provides useful functionality already now. It's appreciated by the beta users, but the sync clients really need further improvement. I think this is where we really have to focus on. So we are heading towards a large-scale sync and share layer for science research. So all our data exposed from day one, massive scalability, high performance, integrated into existing workflows, and we still have all this with a very small overhead on top of our existing operations and development. And still as easy to use as a Dropbox. That's it.
Thank you very much. So let's take one quick question, either to Jakub or to David.
I'm just wondering if you're tracking growth in other services, and you listed Dropbox, but are you tracking growth in those other storage services to determine whether people are migrating to this for the majority of their use? You talk about only 50% uptake so far, but it's really a question of, is this just additive to everything else that's out there, or is it actually replacing the other options?
So currently I would say it's additive because we have a different storage. Okay, and with our beta service, we are nowhere near really going large scale. It's simply the architecture needs to be revised. That's why we started that work. In terms of other systems, I can give you an example of AFS. We are essentially doubling the number of files every year. So a year and a half ago, it was 1 billion. Now it's 2.5 billion. So it's really a huge growth. It's really a huge growth. But this is a very good question. Once we go from a prototype on EOS to a full production, that would be a... But then again, we would just adding this Dropbox-like capability on top of existing storage. So then the interesting thing would be how much of the existing data is accessed in this new way.
Thank you very much. In the end, you will have a chance to give another question, right? So we should move to the last speaker, who is Maciej Brezniak from PSNC. He's also my DF storage chair, and he's talking about, again, a different approach, so they are building something from scratch.
Okay, Peter, thanks for this introduction. I will be speaking on behalf of the whole National Data Storage 2 project consortium, so my name is only name of the frontman. My talk will be about secure alternative to Dropbox-like solutions, because we have seen here the presentation is focused on scalability of the solutions we already have and are popular. I will be focusing on actually security stuff. Oh, okay, thanks. So, instead of introduction, I try to show you some facts, recall you some facts you actually perhaps know very well. It's one of the of my favorite sentences related to cloud, which says actually the same what we think, that cloud is necessary both for service provider and for end users. The recent efforts, however, have shown that we cannot be sure about the safety of the data in the cloud. For instance, the case of Heartbeat bug show this. What's more important, even experts are a bit lost in this world, because in the end of February this year, they told us, guys from Google, Google, Verizon, Microsoft, and security experts told us that cloud is safe enough to use it. But 1 month later, they had to admit that it's actually not enough safe, and surprisingly, the same people appeared in on both sides, saying that once the cloud is safe enough, and on the other side that it's catastrophic what's happened after Heartbleed. So this is a lesson for us, that we shouldn't trust any experts, and we also shouldn't trust actually any technology without checking it. And we should also be aware that our data already in cloud, and we should be very careful what can happen to them. Importantly, in a majority of today's systems, it applies both to public clouds, but also on-premise storage. Data security is only protected by access control. So if the user gets authenticated and authorized, he can get the files. We think that this is not enough these days because of the threats we actually have seen recently. So the question is what we can then do. Of course, we could actually take the data away from cloud, which is not very practical. We could also ignore the threats, which is not very reasonable. And our proposal is to keep the data in cloud, but protect it appropriately to today's challenges. So we were working on these topics during the last 2 years with institutions in Poland and within the National Data Storage 2 project. And we tried to develop a solution which helps you to keep the data in cloud from one hand and still maintain your security. Importantly, this ended up with a set of tools for encrypted storage in cloud. These tools enable different functionalities, starting from virtual file system-like access and storage of the data, which we find a very convenient interface for majority of users and applications. But we also added a synchronization functionality during the course of the project to this the whole ecosystem. We have the graphical interface, which acts as a file browser-like interface. I will show this some screenshots later on. And we, of course, have also some mobile clients, currently limited to Android, but we also consider different on other platforms. Importantly, our solution helps you to combine what actually was also referred by previous speakers. We target to combine different functionalities within one infrastructure. Our idea is to enable synchronizing some part of the data you normally store using file system-like interface, because it's high performance, it's scalable, and it's convenient. But you can be interested in synchronizing part of the data, because this is, for instance, the directory which stores your files which you are working on currently. So this is possible in our system, and you can actually see the changes made by file system clients through Synchronization Client and vice versa. This is how it looks like in practice. You actually, these are configuration panels of Windows client, which lets you mount this virtual drive. It appears in the system like it would be a local drive, and you can also configure session to the server, which is a regular session to the SSH server. Mounting these virtual drives we made under Linux is also simple. You simply run a CryptoFS library, specify login and address of the server. You display you point the mouse point, and you also point the encryption the file containing encryption key. You can also automate this mounting from FS tab using appropriate entries, and you can also automate startup in Windows client, because it can run as a service. Synchronization client lets you define multiple pairs of source and targets directories on the client and server side. Importantly, you can also put your data into confidential pairs, which is marked as under encrypted directory on the server side. And if you make it, actually your data are not only synchronized but also encrypted on the fly. This is the view of GUI client, which is a browser-like client, which enables you to browse through the namespace. You can also see the status of the task you make. For instance, if you click a file, it gets downloaded. You can see how fast it downloads in order to present it to you. You can also see attributes of the files, and importantly, you can also see the files you shared with the others. You also can export some files into web and things like that. So this is, for instance, the window which shows you what's the progress of multiple files download task, which actually helps you to manage these jobs. Like, for instance, you might pause them or restart them, see how they progress. Our synchronization client, our Android client, provides two kind of interfaces. One is file system-like, file browser-like interface, and the other is integration with galleries, things like that, which enable you to actually share the data directly from, for instance, gallery, and you can also see status of the jobs, of the upload-download jobs. So summing up, we have a set of tools which we believe to compose an ecosystem usable for different use cases. What was important on top of the same infrastructure and on the same data. So about security, I'll try to shorten this part because this is well described in the last year's presentation. We actually use symmetric encryption and integrity control. What I would like to you to take from this room as a message is that these days the hardware we have in our devices is good enough to make encryption without losing performance. For instance, on the regular PC, like I have here, you can using the benchmark, synthetic benchmark, you can achieve 1 to 2 gigabytes per second of AAS algorithm, thanks to the fact that Intel CPUs actually fully offloaded to hardware. The same will happen in ARM version 8. Actually, this is now introduced in the markets, and this platform includes the instruction set which offloads the encryption. In addition to encryption, we also integrity control our data so that if some attack happens, you can detect the change of your data. We calculate per logical block digits, and we also encrypt them with files key just to be able to detect possible changes or tweaks on the server side. I will I have more slides. Some slides prepared for that topic, but let me just say at this point, to shorten the presentation, that we have a key hierarchy which involves symmetric encryption because it's fast for massive data, but also asymmetric pair of keys which help us to do fine-grained file sharing and also help us to avoid users having the files for having to keep the keys for every file he has stored in the system. So they are actually per file keys are unique, generated by us and also by the client application. They are stored in the system, however, encrypted with users' public key, so that only users, the same user holding private key, can decrypt the key, which is the key for the file, and then he can decrypt the file. I will skip more complicated setups because of time, and of course, when we speak about security, we can of course say that it might be not efficient enough. So our statement here would be that based on our experiments, and part of them will be present here, we can state that if you use appropriate hardware, actually normal CPUs these days, algorithms and also implementation language, you can really achieve a good performance of security-enabled solution. And our tests show that our secure clients keep pace even with insecure solutions. For instance, there is a quite surprising result we got while doing it is kind of killing test for synchronization. We used a Linux kernel source tree, which is something like 45,000 of files, and we synchronized it up to the server and downstairs. So we see that even encrypted CryptoBox solution, which is our synchronization client, is faster than, for instance, ownCloud while doing only plain storage, which is unsecure, and it keeps and our client keeps pace with PowerFolder with Boxcryptor version 2. Boxcryptor version 2 is important because we not the one named Classic, because only this one has this key hierarchy we are also using, which is both safer and also more flexible while it comes to sharing. What's important for the end users might be CPU load. So we try to avoid how good is encryption and how if the encryption has an impact on the client load, and you see that the green line is actually a little bit higher than the blue line, which is our CryptoBox without encryption. However, this change is not that big. So we could say that we must give up with encryption because of performance penalties. Important observation is that the implementation we made within 1 year actually is much lighter than the implementation made, for instance, by ownCloud, which takes 8 minutes, makes 8 minutes loads on the client while doing our killer tests. We see this is a serious limitation, and we think that the lightweightness of the mechanism we use is also kind of advantage. When you go to the encryption of the file system-like access, on top of the file system-like access, you can see that CryptoFS encrypted performs slower than SFTP NetDrive, which is a popular solution to use to make disk-like access to unencrypted data, combined with Boxcryptor Classic. But again, this solution used only one key for the whole set of data. In our case, we use different keys so that we should compare ourselves to Boxcryptor, and we see that our solution is many times faster. When it comes to bulk data transfer, you may see that it's also good enough to compete with other products. So the conclusion from here is not only that we did our job well, but it's also that you can encrypt, so you can be safe while being while having good enough performance and having low overhead on your infrastructure, because you must keep in mind that client-side encryption causes that we actually spread the load related to encryption over all clients. We don't do it on the server for security, but it's also a performance or scalability advantage. So you can always ask how easy or how difficult it is to deploy or scale our solution. And we think that the solution we made is actually easy to scale because there's any complicated software stack on the server side. Previous speakers already shown us that having database on the backend is actually challenging. It helps us to make some functionality but to implement some functionality. But scaling LAMP stack or databases is much more difficult than scaling, for instance, file systems. Of course, you may argue here. However, we have to keep in mind that in many situations we'll actually add the solution to existing infrastructure. For instance, in the case of PCC, we have GPFS-based storage clusters. So it's really easy to scale using existing solutions, also existing knowledge. Functionality-wise, we have low requirements. It helps us to run these solutions I presented on top of any storage which exposes SFTP. So it's really easy. We think it's really easy. You can run it on top of Linux just after installing it. Perhaps it already includes OpenSSH server. It's the only thing you need. And what's also important, we can use the user management systems such as LDAP and Active Directory. And we also are trying to find a way to be able to have the right access to our applications, but it's for now a bit changing because this is a non-web application. Yeah? So, okay. Let us stop for a while on this in deployment things. For instance, on this in exhibition area on our booth in Pioneer booth, we are running the small installation of our solutions using really compact low power server. You can of course scale up using rack servers. You can also run this solution on top of virtual machines, and actually what you need is to ensure the file system replication. We believe that it's really easy to run, and I hope it's also easy to use. So what's also important, this simple deployments unshown are not the only option. We are now piloting in Poland the deployment of our synchronization clients in front of the large-scale storage infrastructure, which provides 14 petabytes of tapes and disk storage to our academic community. And we are now piloting the deployments where we can actually use all this functionality starting from visual file system like encrypted storage and data synchronization. Implement this functionality on top of this big infrastructure. And this thing, by the way, makes geographical applications. So we have these things kind of given by the external solution. Yeah? So one of the important things I would like to also you to remember from this presentation is that our view in PSNC, but also in some other environments, is that we as environments, as service providers, we should somehow try to position ourselves on the market versus the competition. Maybe not only competition, also collaborators. But we think that we should have a golden alternatives of popular services, and this golden part of our service could be security, and should be security if we are responsible for the data of people which actually deposit them to us and they trust us. And we hope that the community is open enough to adopt these services we propose, because we are aware that they're not plug and play in 1 second, but they offer added value, which is security. And we also think that we should actually try to educate our users and increase user awareness of security issues instead of hiding it behind the marketing phrases. Yeah? Okay, so to conclude, I would like to say that we spent a lot of time on making the secure alternative for popular storage and synchronization solutions. We think that it's transparent in terms of performance. It has convenient interfaces such as virtual drives and things like that. Low performance overheads. Of course, the specific solutions. So we think that our niche are security-aware environments and those applications where security is really a must. And we started with solution targeted to safe storage of massive data. Really massive data like backups, like archives, because this is actually initially planned as added value of our popular archive service. And then we migrated into online storage things and also added synchronization functionality. We don't have a fancy web interface yet, but it's still an open issue. So once again, the message that we believe that we as an environment and we as service providers should try to deliver our clients nice, not only nice, but also secure applications. And we should also avoid non-scalable solutions, because at the end, this will be a problem for us. Coming to the question if our solution can be reused, I think so. If you would like to argue with me, I invite you for discussion, and we are also present on the Pioneer booth. And last word about further developments, we consider covering new platforms such as Macintosh, Windows Mobile, and iOS, and also consider possibly supporting different backend protocols, which should be relatively easy due to the logic we already have kind of abstracted. So you're invited to try our solution. You can go to the website, you can download our clients, you can also find the information there how to enroll to the pilot installation we have. And if you have any questions, you can visit us on the Pioneer booth.
Thank you very much. So we are running over time, but just 2 quick questions, maybe either to Maciej or the previous speakers.
Fit in time.
Question to David. For CERN solution, I'm a little bit confused. I think here for the storage, we have 2 types of storage. We have storage as a service. That's where we deploy it to persons, okay, on their daily need. But we have a storage and infrastructure. This is what could be big file systems for research and for repositories for research and other on. Here, what I see from your solution that you are combining both. I don't see where's the interest to that people should look at files or enter to files, big files, for example, for research from their mobile or from their Android using Dropbox-like solution or something like that. But for personal files or for documentation, for something like, I see big interest here that we have our hard disk with us everywhere. But for research purpose, I don't see the interest that you are merging both solutions in one.
Okay.
Yes.
We have extremely creative users, and I can imagine many different ways this can be used. So I don't know, just on top of my head, an example. If you have bad jobs which are doing data analysis and then they are producing histograms, and they are stored histograms are stored in, I don't know, files, and these files go to the storage system, and then they would be also automatically synced to your laptop, for example. So as soon as your jobs finish, you can have them synced to your laptop for the offline access if you need.
That's
okay.
Results, not the main.
For example, the results. But you can also imagine very, very well the other way around. You prepare something, you collaborate with your colleagues, you prepare some input files, okay? And you prepare them on your laptop while you're at the Terina conference, and they are synced to the system, and they are then ending up in the storage, and they are there for your collaborators to use, and then maybe an input to some other bad jobs.
All right.
You know, it can be integrated in many different ways. Of course, you don't want to have a petabyte of data synced to your laptop or to your Android device. That's obvious, right?
All right, so let's take this discussion offline during the break. Thank you very much for all the speakers to come.
Yeah.
All right. I have a couple of announcements, otherwise I'll